Now, we've been talking about analyzing the simulations, and we've bifurcated things into terminating and steady state. We've been talking about terminating. We're going to go into that in a little bit more detail today, especially as far as implementation goes. I showed you one implementation yesterday, and I'm going to go through another one that's a little bit more involved, just to kind of show. And then at the end of today, I'll start peeking at steady state, and that will continue next week. What's on tap for tomorrow is, as you might guess, I'm going to have you do one of the things that I've been demonstrating. So, okay, so just as a reminder, the idea of a terminating simulation is that there is some kind of either natural or imposed end condition. There are some simulation models that by their very nature have an end state. One example to kind of think of with that is a kind of just an imagined combat model, let's say, where you have two forces that are interacting with each other. Some of the forces get attrited, and one natural ending condition, well, one sort of extreme ending condition is that one of the forces gets completely wiped out. I mean, that would, and then after that, it's clear that no further events of any interest would take place. I mean, typically, the kind of ending conditions that such scenarios have to do with either like some kind of force ratio type of situation, or maybe one side loses when they've lost a certain percent of their forces. Another natural ending condition is more of a maneuver type of thing, where let's say one side has a goal of achieving a certain objective, that is getting their forces onto a particular location, and then the other side has the objective of preventing them from doing that by a certain time. Again, these are all conditions which are kind of natural in the sense that they're built into the dynamics of the model. For most of the models we've been looking at, though, there is no natural end condition. In other words, just thinking of our multiple server queue, you can run the bejesus out of that. That can just kind of run forever. So what would be a typical ending condition for that would be a situation dictated by the situation you were modeling. That is the facility. If you were modeling a facility and that facility operated only under certain hours, so we would say open in the morning and close sometime in the afternoon or evening, then when it opened, it was empty and idle. I mean, that's the initial state that all of our multiple server queue models have been in. And then when it ended, then there are actually a couple of choices that one can make on that. One is to just kind of end it and just take the situation it is, and that's what we're going to be doing. A more realistic, perhaps, model of that would be to use one of these arrival processes that stopped after a certain amount of time. And so in that situation, the customers would stop coming in, but any customers that were in the facility would be allowed to get processed and leave. Again, we're in the models, the model I did yesterday, and then also in the model I do today, I'm not going to do that. But that may be something I may make you do. So again, what I mean by that is a situation where, to represent the way the facility would operate, it would be that at closing time, what you would typically do is sort of lock the door so that nobody could come in. But for the customers who were in and getting processed, they would leave and you'd open the door for them and then kind of lock it behind them. So in other words, a model like that would shut off the customers that were arriving, but continue to process the events until everything emptied out. Again, I'm not going to do that today, but so in our model today and yesterday, what happened at the end of the day, we sort of locked the doors and basically shot all of the customers who were inside, because the next day when the facility opened again, everybody was gone. So that's a characteristic of the model. And again, keeping in mind this caveat that all models are wrong, and yet some are useful, despite the fact that this is what our model is doing. Actually, no individuals are actually harmed by the simulation. And the question is, does doing things in this manner actually affect the results? That's a question that one could only answer by doing it both ways. That is, by running the model as we've been doing, and comparing that with the same situation where you run the model and only cut off the arrivals, but then allow everybody inside to continue to get processed. So again, these are the kinds of issues that one has when doing a simulation study. And in fact, it is typical that when you develop a model for a customer, a client, as it were, the model will typically just engender more questions rather than answers necessarily. Or what would happen if we did this, or what would happen if we did that? And all of these are questions which are triggered by the model itself. In other words, the initial questions are one set, and then the model itself produces more questions. So one quote on this is, there are never any answers, only just more questions. So that's okay. So what are the one important property, and one of the things that distinguish terminating from steady state, which we'll get to in a little bit, is this, and this is an important thing to understand. In a terminating simulation, all of the measures are affected by the initial conditions. For our queuing models that we've been dealing with mostly, those initial conditions are the fact that it starts off empty and idle. In other words, at the beginning of the day, there are no customers present. That's an initial condition. And if we're running our model for a relatively short amount of time, as we've been doing, say for a day's worth for each replication, then our measures are going to be affected by the fact that we started empty and idle. The real impact of that are going to be in things like the delays in the queue and the number in the system and things like that. Those are going to be, in general, probably less than if we ran our model to steady state, as we'll talk about later. But nevertheless, the measures are affected by the initial conditions. Again, with our hypothetical combat model, the outcome of that are clearly affected by the initial conditions. What are the initial conditions? Well, among other things, the size of the initial forces. So if you are manipulating the force structure and then running a combat model, then that's clearly going to affect the initial condition, affect the measures that you have. And in fact, many times, or like one way that a simulation model could be useful in that respect is a question of how much do we really need in order to guarantee a certain probability of success for this? That's the type of thing where you could manipulate those initial conditions and come out with some recommendations in terms of this much force would be required in order to achieve the objective with a certain probability. Okay, the second thing, and this applies to all output analysis, is that we at the very least, and this is at the very least, we want a confidence interval. You should understand it's not enough to just run one replication. It's not enough to run multiple replications and only estimate the mean, because even with an estimate of the mean, we don't have any idea of how representative our estimate of the mean is relative to the unknown value that we're trying to estimate. And so in order to do that, we need an estimate of the variance. And the problem is that we don't have independent, identically distributed observations. We cannot do this accurately. In other words, particularly if our observations are correlated, then our estimate of the variance is biased, which means, and in fact, typically in many simulation models, there's a positive correlation between the different values. And yesterday I kind of walked through a little thought experiment as to why delays in the queue might have a positive correlation. In other words, if one customer has a higher than average delay in queue, the chances are greater than normal that the next guy would have a higher than average delay in queue. In other words, information about one customer's delay in queue gives you information about the next customer's delay in queue. So that's the opposite of independent. Again, the contrast to that is thinking of flipping a coin or rolling dice. Successive rolls of the dice or successive flips of the coin do not depend on what happened before. Okay, so the problem the problem with terminating analysis, though, is not so much that as how we define our output measure. And again, notice the double modifiers here. So the expected average delay in queue. So what does this mean? The average delay in queue was the average over, let's, in our case, say 1 day or the period. So this would be the average over 1 day. And in other words, each customer who comes in actually has a different distribution, a different problem.
We can't see your, sorry to interrupt, but we can't see your screen, whatever you're trying to show us.
Oh, you can't? I thought I was sharing the whole thing. My apologies. I was going along here. Okay. Sorry. Let's.
A few moments later.
Is that better?
Yeah, that's good.
Okay, so this is what I was talking about. Okay, so again, expected average delay in queue. The expectation is over, well, the average is what we've been computing. Each customer has a different probability distribution for their delay in queue. And so actually to take the average and think that that's some estimate of the mean, it's what does it mean to take the average of observations that don't have the same probability distribution? So normally we think of the sample average as estimating the mean of something, but the presumption that only occurs if the underlying probability distribution is the same for each observation. But here, each delay in queue has a different probability distribution. I mean, in particular, the very first guy in is always going to have a 0 delay in queue. In fact, if I have K servers, the first K customers are going to have a 0 delay in queue, and then the next one is going to have a distribution which could either be 0 or some other value. It's after the first K guys, the expected value is going to be positive. And what typically happens, a typical thing, if this is K and this is delay in queue for the ith customer, it tends to look something like this. If this is the true expected delay in Q. So this is the kth guy. He's going to have 0. The K plus first guy is going to have some expected value. Let's put him right here. So the K plus first guy is going to have some expected value, which is positive, but tends to be fairly small because there's a good chance that he could actually be 0. And then the expected value continues to increase. Now, it may be that when we end our simulation, we're right here. And so if we were to continue it for a longer period, then it may be that the thing will level off, or it may be that our it may be that it actually looks more like this. It could blow up for all we know. We don't know. Why? Because we've stopped it at 5 o'clock and let everybody out. And so we don't know what our system is going to behave if we kept it going for a long period of time. We don't know that. So in steady state analysis, as we'll take a look at shortly, it's actually a little bit simpler to define what that output measure is, but it's a little bit more tricky to try to get to it because for a variety of reasons. So our procedure has been to perform independent replications. We need to ensure that the initial conditions are identical. How do we ensure that? We ensure that by making sure that all of the reset methods set all of our state variables back to their initial values. That is, our queues are always empty or 0. Our available servers are always equal to the total number of servers. And whatever other state variables we have are all set back to their initial conditions. That's why that method it's called reset, because after every replication, you need to basically reset all of your state variables. You don't need to reset your parameters because your parameters are not changing. In other words, for our multiple server queue model, the number of servers stayed constant. So that doesn't need to be reset. It just stayed the same. Our random variates did not get reset because if we reset the seed of our random variate back to where it was, we would get exactly the same value on the next replication. So we don't reset the random variate seeds. We just keep them going so that we get an independent replication. So if we assume the initial conditions are identical, we can therefore estimate our variance from independent, identically distributed replications. And that's what we've been doing. So what I wanted to do is just give you a slightly more extended example. This is our server with Renege's model that we did a while back. And so I want to look at all these different measures. I want things like the expected average time in the system for those who got served, the expected average utilization, the expected average number in the queue, the expected average delay in the queue for the customers served and for the reneging customers. Remember, those were different. And then the expected percent of reneging customers at the end. Again, those were all values that we were measuring. And so how do we wind up doing that? Okay, so in the code, in my GitLab code, there's a new class called Test Confidence Interval 2. This is the second one. And what it's doing is it's using the server with Renege's model. Okay, just to review how we go about doing this. One is because I'm going to be using 2 of the random variates that I implemented, the triangle and the trapezoid. I need to tell it to add the search package for my random here. And so what I'm going to do is I'm going to have my inter-arrival time generator, which is going to be a triangle distribution with these values. Again, where did they come from? They come from somewhere. Where these values come from is something that obviously has to be dealt with if you're dealing with an actual situation. For our purposes, we're just going to take them as given. Our reneges, we'll keep those uniform 0 to 4. And our service time, I'm going to use this trapezoid distribution that we implemented. That's a fun distribution. And what's nice about what the trapezoid does, if you remember, it had this trapezoidal shape. And so what that, and then it had a sort of a long, well, in this case, not so long, but here you're going to have some very low values between 4 and 6. You're going to have a few high values between 7 and 8, and then it's going to be kind of flat between 6 and 7. So that's a fairly longer type of thing. Okay, so now we're going to start with one server and just sort of see how that goes. And if you remember, for this model, we were putting everything into the customer arrival process. Just as a review of that, let's sort of see what was going on with that. We were extending arrival process, but we were generating the service times and the renege times from our customers. So when where are we? Okay, so when an arrival happened, we instantiated a customer. And what happened with the customer? That was an entity that had a service time and a renege time. And okay, and I just had getters on this, so I made those protected. And so our arrival process, again, we extended arrival process, and at arrival, we simply called the super to get another arrival, and then we scheduled our arrival with the customer. Our server with reneges, again, this was the model that you all did. And that was just a sim entity base. And the idea there was that, okay, here's our reset method. That's something that we always need to do. The property changes, etc. And then the idea is that at the arrival, we would schedule the renege event. But then at start service, we would interrupt it if we made it to start service. Whereas if we actually reneged, we would remove that customer from the queue and then increment the number reneged. And here we could get the delay in the queue for the renege guys. Okay. So up until here, we're simply setting the model up. Okay, the sim event listener, our server with reneges is listening for our customer arrival process. And now we need to, there are two sets of statistic objects that we need to define when we're doing this analysis. One are the inner ones and one are the outer ones. The inner ones are ones which collect for every they're the ones which collect for every state variable that we're looking at. So we had one for the queue. We had one for number of available servers. We need that for utilization. Okay, the delay in queue for servers served and reneged, and then also for time in the system. So these are all connected to state variables that are being fired by the component. And in order to make that live, we have to add each of those as a property change listener to our server with reneges. There's no need to add any property change listener to the arrival process because there's no state variable there that we're interested in the time. Well, I mean, we might be, but it's really not very interesting. The most we might be interested in for the arrival process are how many arrivals have we had, and we're actually going to have to use that at some point for the to do our value. Okay, so then the outer statistics are the ones which we need for doing our analysis. And these do not, even though they could, they don't listen to anybody. So these, what we do is we insert them by calling new observations. They're not done by the property change. Why? Because we're doing those kind of in the code after we run each replication. And now normally there's going to be one for each of these stats, but then there's one additional one. So, okay, so here's the outer number in QStat. And then actually the names aren't important except for keeping track of what's what. The timing system, utilization. Again, utilization, we're gonna have to do a little dance. And then here's one which does not correspond to any of the inner stats, and that's the percent renege. So we want to know, one of the things that's actually one of the reasons why we have a model like this is we want to know if we run under this circumstance, what percentage of customers are we losing because of this impatience? And that's an important one, but there's no inner stat for that. How do we get the percent renege? We take the number of reneges and we divide it by the number of potential customers. And then the delay in queue, those are fairly straightforward. Okay, so for this facility, I made a 10-hour day. So our stop time is going to be, our units, I'm going to postulate are minutes, and our stop time is going to be 10 times 60 minutes. And so we're going to stop at that time. Again, if there are any customers left inside, then too bad. I'm going to hard code 50 replications for this. That's yesterday I showed you a way we can do it from the command. We can have a nice default, but we can also manipulate from the command line. That's a very useful thing, but I got lazy for this. Again, it's always a good idea to print out our components to make sure we're getting the right values in. It's also a good idea before we run anything to say, okay, here's what we're about to do. We're going to run for this many replications of this many time units each. Okay, it's important to do that before we run, because if it bombs out in the middle here, we get a little bit more information about what it was trying to do. So for example, what could go wrong? Well, somehow I could have fat fingered the number of replications. Maybe it came in at 0 and I wasn't getting any results. And so if I say, well, that will show up here. If I fat finger number of replications, I'll see it right here. Okay, so we want to do independent replication, so we wrap the whole thing in a for loop. And it goes more or less the same, and this is the same structure as in yesterday's model. It just there's more stuff in here, so that's important to dissect this. So we always start by resetting from schedule. What that does is that resets all of the state variables that are hanging around back to 0, and it also puts the run events on the event list so that we're all set to go, but it doesn't execute things yet. Then we need to reset all of our inner stats. Let's see, what am I looking at? Okay, so for some reason, the delays in the queue were not reset. Okay, those should be reset. And then after we've reset all of our inner stats, see now everything for this replication is back to a pristine state. Our state variables are in their initial state. All of our inner statistic objects are in their initial state. And now we run the simulation. Excuse me. Okay, and How do you know when the replication is over? When you return from start simulation. And when we're done, when that happens, then we can pass the inner stat values to the outer stat values. So the number in the system, we take the inner, number in the queue, we take this is the inner number in the queue stat, and we're looking at its mean. And keep in mind, we don't have to do the mean. We could do the maximum. We could even do things like the variance or whatever. It's just not clear what that would mean. The maximum would be a more interesting one. Okay, again, time in the system, we take the inner time in system, get its mean, and pass it to the outer one. Okay, now for utilization, we need to compute the utilization. And here's what we're doing here. And utilization is often done on a 0 to 100 basis instead of 0 to 1. And so we take 1 minus the number of available servers divided by the total number of servers, and that will give us our utilization between 0 and 1, multiply it by 100, that gives us a value between 0 and 100, which is, again, more typical. And now for the percent reneges. Now here we have to be a little careful because the number of reneges and the number of arrivals are both integers. So if I notice what I'm doing, I'm multiplying the whole thing up front by 100, 100.0, not 100 integer. You just need to be a little careful. This sometimes bites you because of the way that Java works. Integer division is integer division. And in this case, it will give you 0 if you don't watch out. But as we all know now, what happens here is I take a double, I multiply it by an integer, that promotes this expression to a double. And then when I divide it by an integer, I double divided by an integer is a double. So this whole thing's going to be a double. And then for these guys. Okay, so this business is a bit new, or I mean, it's what we did yesterday, but here's where, like, you know, here we have to do a couple of extra computations, like for the utilization and particularly for the percent reneges. Okay, so here I decided to have an alpha of 0.01. What are the standard alpha values? 0.01 and 0.05. 0.05 seems to be the most popular because that's sort of the easiest, but 0.01 gives you wider confidence intervals, but it gives you sort of a tighter, a larger amount of confidence, because now my confidence level is 99% rather than 95%. Okay, so here's and confidence is typically expressed from 0 to 100. So either 99 or 95 are two of the most typical ones. The other value that we need is this quantile from the student T distribution. And since the number of replications is going to be the same for everyone, I can use the same student T quantile. So rather than doing that lots of times, I'll just sort of do it once. Now I compute the half-widths. And remember the formula for the half-width, standard deviation divided by the square root of the number of replications times that student T quantile amount. Okay, so here's my confidence interval for the time in the system, the number in the queue, the utilization, the percent renege, and delay in queue for served, and then the delay in queue for reneged. Okay, so let's run this, and it runs pretty fast, mostly because we're running for a very short amount of time. If you remember, when we ran for like 100,000, it sometimes took a few seconds. Okay, so here are our confidence intervals. And to print them, you know, we had I printed the confidence, and that's what showed up here, because then I can change the alpha value. And then I just get the mean from the outer stat as the center value, and then the half-width is sort of the plus or minus. So let's let's sort of take a look at this. And I mean, at first, it doesn't seem like we're doing terribly badly. Our time in the system isn't too bad. Look, the number in the queue, that's not a bad number. 1.5 guys. It's that half a guy you got to watch out for. All right, let's look at the delays in the queue. Okay, so for those served, they waited about 2 minutes. Interestingly, the ones who reneged seemed to wait a little bit longer. I hope I didn't. Let me just make, yeah, no, I was getting the right ones. Okay. All right. So if we're just looking at like our delays in queue and then the number in the queue and even the time in the system, can remember that for the time in the system, you always have to have the amount of service time that you have. So where the slack is how much time you spent in the queue. But there are some red flags in this. Okay, there are 2 red flags here, and then these are something that you need to kind of look at if you're looking at models like this. The first red flag is this utilization, like 99%. That's pretty high. So like 99% utilization is an indication that things are not so great. Now, if you're the owner of a facility, you want to see your machines always running. You want to see your workers always working. But nevertheless, if utilization is this high, then that usually means that the queues are getting big. But in this case, our queues aren't getting big. I mean, the delays in queues are actually quite small. The number in the queue is a reasonable size. So what's happening here? Well, look at the percent reneges here. 71% of customers are renege. That means that we're losing more than 2/3 of our customers. We're losing almost 3/4 of our customers who are getting impatient from waiting online and leaving. All right, so this is the red flag here. So this is why you need to look at many different measures when you're analyzing these models. Because if we were only looking at the queue, which is a normal place to look, then the queues are doing fine. But again, the high utilization is a red flag, and certainly having 71% of customers reneging is definitely not a good thing. Okay, so what can you do about this? There are really only a handful of things that can be done. Let's see. First, we can say, oh, screw them, the heck with them. They don't like us, too bad. Or we could say, well, we just need our servers to work faster. All right, how can we do that? Well, we can, what is that saying? The floggings will continue until morale improves. Okay, so kind of going back to here, we can look at our service time and you can say, well, again, where did this come from? Presumably this roughly matches what we're observing. How can we get our servers to work faster? If there are machines, we could try to upgrade them or get faster machines. If they're servers, we could try to, if they're people, we could try to introduce additional training or maybe find improved operations procedures that might help that. Or we could just hire more. So look at what happens. What if we hired one more server? So instead of one server, we now have 2. Let's see what that does. Okay, so now look, our queue statistics, everything is improved. Our time in system has gone down, but only by a little bit. Likewise, our queue measures have gone down, but only by a little bit. Our utilization is still very, very high. And remember, this is per server. But our percent reneges now are down to 43%. So we've almost cut our lost customers by, in half almost, simply by having one more server. And 43% is still a ridiculously large amount. So what would happen if we had another server? Okay, so again, our measures are improving, but not by a whole lot. Even our delays in queue are, I mean, they're going down, but not by a whole heck of a lot. However, our utilization is still up in the stratosphere, but our percent reneges are down to around 15%. That's still a bit high. I mean, I would still want to keep hiring people until things all of a sudden now when we go from 3 to 4, we're now actually not, the percent reneges now are negligible. Again, our time, our queue sizes are negligible. All this is negligible. So now is it worth it to hire that extra person? I don't know. I do know that in almost every case, it would be worth it to hire at least 2 more. I mean, assuming that would be feasible from an operational standpoint. Again, look at what happens to the utilization. It goes down to 87%, a significant reduction. But more importantly, we're now really not losing anybody due to impatience, and people in the queue are just not happening. Okay, so this is the kind of thing that you want to that we can be playing with, and in fact, notice what we're doing. We're manipulating some of these input parameter. We've manipulated just one input parameter and looked at a number of different values. And that's now the next step in that is something called design of experiments, which we don't have time to really get into, but that's something which is a very important area, which allows you to take these models and really extract a lot of important information from it. Okay, so that's our server with reneges example. And just to take a peek at what we're going to start talking about next week is steady state. So all of this was operating on a terminating model where we start with a certain set of conditions, we run it for until a certain set of ending conditions. In this case, the ending condition was simply the stop time, the end of the day. For steady state, we go beyond that. In steady state, what happens is we run our model, the model runs until it reaches, well, steady state. And what does steady state mean? Steady state means that the simulation is fluctuating around, like each state is fluctuating around a single value. In other words, each of our measures, such as our delay in queue, is going to have one single value that it basically settles down to, or it blows up. It'll either blow up, and we'll find that out soon enough, or it fluctuates around this single value, and that single value is what we're after. So our objective is now to estimate what that unknown value is, and that's now just a single value. A key difference between steady state and terminating is that the steady state measures do not depend on the initial conditions. The terminating ones do, the steady state ones do not. And so one of the issues that we have to first deal with is, well, does it reach steady state? When, if at all, does it reach steady state? Now, steady state is really an asymptotic thing. So in a sense, it it literally doesn't necessarily ever reach it. It gets close enough for all of our purposes, really. Just like, well, you remember in mathematics what an asymptote is? So like an asymptote would be a situation such as our exponential, where it kind of gets closer and closer to the origin, but never actually reaches it. But it gets there for all intents and, it gets close enough for government work, as it were. Okay, so that's what we're going to be after next time.